We have characterization of closedness. Closedness in a topological space. Yeah. By the way, these conditions are many, because also that one is an if and only if statement. So when you look at that, we are saying that a subset of a topological space is closed. Subset of a topological space is closed if and only if it is contained in the set. So we are letting A to be a subset of a topological space X, making an assumption that A is closed. So we are saying that A is closed if and only if the boundary of A is closed if and only if the boundary of A is a subset of if and only if the boundary of A is a subset of A. So suppose that A is closed, so this implies that the closure of A is equal to A. Complete the boundary. By definition, boundary of A is A closure intersection this. Now this is equal to A closure is A intersection X minus A closure. Observe that. What do we observe? Observe that the intersection of any two sets, the intersection of any two sets, if you are having X being A intersection B, the intersection is always a subset of A, and as well it's a subset of B. So this intersection is a subset of boundary. Sorry. The boundary is the intersection. The boundary is the intersection. The boundary is the intersection. So this implies that the boundary of A is a subset of A. The intersection is always a subset of each of the two sets. So we have proved the forward direction. Backward direction, suppose that the boundary of A is a subset of A. Now we show that A is closed. We show that A is closed. Suppose that the boundary of A is closed. We show that A is closed. So we are supposed to show that the closure of A is equal to A. We are supposed to show that the closure of A is equal to A. We are going to prove this by contradiction. So by way of contradiction, suppose that the closure of A is not equal to A. Is not equal to A. So if these two sets are not equal, that means if they are not equal, there exists an element here which is not in A. There exists an element in A. So this implies that there exists X in A closure and X not in A. You can as well say that there exists an element in A but not in the closure, but not in the closure. You can say that there exists an element in closure of A and that element is not in A. You can as well say that there exists an element in A, not in A closure. Yes, without loss of generality, I'm considering that one. I'm considering that one. So what do we know? So this implies that X is in closure of A and X is in X minus A complement. So X is in closure of A and X is in the complement of A, and we know that this complement is a subset of X minus A closure. So X is in A closure and X is in X minus A closure. and x is x minus a closure. That's the implication of this. This is a subset of that. So if this is in here, so it's also contained in there. So this implies that x is in a closure intersection x minus a closure. So x is in the boundary of A, and by hypothesis, what is that hypothesis? The hypothesis is that the boundary of A is a subset of A. By hypothesis, x is in A. X is in A. This is a contradiction. Because our assumption was x is not in A. We have arrived at something telling us that x is in A. So that implies that our original assumption was actually wrong. So this implies that the closure of A is equal to A. But subscribe, guys. Kindly subscribe to the YouTube channel for more interesting stuff on topology, group theory, applied chemistry. Yeah, we are still coming. We are still cooking things. Yeah, with time I think we shall be good.